there in the core company, then power system stability plays power system stability plays a very major role, and power system stability needs to be analyzed at a very systematic way so that we can understand what power system stability is and how does it relate with the um, problems which arise in the power system due to various reasons. As you all know that before few days back there was a power system failure in the Mumbai link, Padge Mumbai link, and we have already taken the case study of that in our one of the lecture of the electrical power system. Today we are going to have a detailed analysis of this power system stability, and also we will see few questions which are repeatedly asked in the gate examination. So, talking about the property, if we want to talk about the power system stability in its definition sense, then we can write that it is the property of the system that enables it to remain in the state of equilibrium under normal operating condition and to regain an acceptable state of equilibrium after being subjected to a disturbance. So, please note all these points in your copy so that you will be able to know this, because sometimes these questions are asked in the competitive exam related to the definitions even. So we have to know what these definitions are, and we have to understand this definition accordingly. So if we want to define a power system stability, the power system stability is the property of the system that enables it to remain in a state of equilibrium under normal operating condition. So what do we mean by this normal operating condition? The normal operating condition means the state of the system before any type of disturbance or before any type of faults which occur into the system. Like we have already seen various faults, that is symmetrical and unsymmetrical fault. In the symmetrical fault we have seen the three phase and three phase to ground fault, as well as in the unsymmetrical fault we have analyzed the line to ground fault, double line fault, and double line to ground fault. So whenever there is a fault into the system is not normal, or the system is not in its equilibrium position, right? So we have to understand this. What is the meaning of equilibrium? Equilibrium means all the generation which is happening into the generation power plants, they are in synchronism with the loads. That is always the frequency of the grid. That is in our India we have the grid frequency as 50 hertz. So this grid is to be balanced, or this grid should be balanced. Then we can call that the system is in equilibrium state. But as we all know that in a system, if we consider the various parts of the system, no system can remain in synchronism forever. There will be disturbances occurring into the system. Disturbances can be due to various reasons. Disturbances can be because of the short circuit failures. It can be due to the less generation and more load, or more generation less load. Any kind of situation can become a problem for the grid. So whenever there is a disturbance in the grid, we call it the not equilibrium position, or the system is in disturbance. So under the normal operating conditions, when we call that the system is in the state of equilibrium, that means the frequency of the grid is 50 hertz and all the generation station are in synchronism with the grid. So this is what we understand by the equilibrium position. So under the normal condition, the system should be in equilibrium position, and whenever there is a disturbances, like we have rightly said, that various types of faults and other issues into the power system. Because of that, whenever there will be a disturbance into the system, our system should be capable enough to overcome that disturbance, and it should again become it should again regain an acceptable state of equilibrium after being subjected to a disturbance. So this is what we understand by the power system stability. Then power system stability is applied to AC electrical power system only. So whenever we call that the not if the equilibrium position is getting disturbed, that means the frequency of the grid is getting disturbed. So we all know that the DC power doesn't have any frequency, right? So if the DC power doesn't has any frequency, then there is no question of the power system stability in the DC electrical power system. So there are other issues in the DC system. When we have the DC system, there are other issues which come into the power system that you all will learn in your next semester if you opt the elective of EHV, and HVDC transmission system. So there you will learn what are the various parameters of the HVDC system. So as of now, what we can understand is power system stability it deals with only the AC electrical power system. And again, the various synchronous machines remain in synchronism or in step with each other in case of the power system stability. So, this is the very broad definition of the power system stability. We will again quickly recap the definition and we will go ahead. So, you all simultaneously note down all the points one by one which we are taking here. So these are very important points. These points are many times asked in the competitive exams in the multiple choice questions in the form of multiple choice questions. So at that time, if you understand the very basics of the thing, then you can very well write the proper objective or the proper multiple choice question in that particular exam. So again, we will quickly recap about the power system stability. So what is the power system stability? Power system stability can be defined as the property of the system that enables it to remain in a state of equilibrium under normal operating conditions and to regain an acceptable state of equilibrium after being subjected to a disturbance. Power system stability is applied to AC electrical power system and the various synchronous machines remain in synchronism or in step with each other in case of a power system stability. Next, let us classify the power system stability. So, the power system stability can be classified in two parts, broadly in two parts. The first is the small signal analysis, and the second one is the large signal analysis. So, in a small signal analysis, again we classify it in two parts. The first one is the steady state stability, and the second one is the dynamic stability. So, in case of the small signal analysis, the samples or the signals which are to be analyzed, they are analyzed up to 30 seconds. So this is a very important point. This you have to remember. So whenever we analyze the power system stability in a small signal analysis, that is steady state stability and the dynamic stability, those are carried up to the 30 seconds. So as you all know that we have the AC in the AC system we have a sinusoidal wave, right? So if the frequency of our grid is 50 hertz, it means that in 1 second this wave is moving 50 times. So this is what we mean by the 50 hertz frequency. So whenever we analyze the system for the power system stability, you all know that whenever there will be disturbances in the system, whenever there will be faults occurring in the system, whether it is short symmetrical fault or whether it is unsymmetrical fault, it will not remain in the system for very long time. It will be with for a fraction of second, right? So like if we consider thunderstorms and lightning strikes or the surging arrests, so that will be for a very fraction of seconds, and within that fraction of second, if the fault has occurred into the system, you all have already calculated the level of the fault current which will flow into the system. So in case of a three-phase fault, the level of the fault current is very high. In case of the line to ground fault, it's the least affected or the least type of the fault, that is the line to ground fault. Then in the hierarchy, it is line to line and then double line to ground fault. So such type of fault is very we'll look into the analysis. When we analyze this into the category of the small signal analysis, the analysis which will be carried up to 30 seconds will fall under this small signal analysis, that is steady state stability and the dynamic stability. When we come to the large signal analysis will be considered in terms of the transient stability, and the transient stability analysis will carried up to 1 seconds only, because transient stability is has to deal with a very rapid changes in the disturbances or the rapid changes in the system because of a sudden disturbance, and this will be carried up to the 1 second of the system. So this is the classification of the power system stability. Power system stability is classified in two parts, broadly classified in two parts, that is small signal analysis and large signal analysis. Small signal analysis again is classified in two parts, that is steady state stability and dynamic stability. And large signal analysis is classified as the transient stability. Small signal analysis is carried up to 30 seconds, and large signal analysis is carried up to 1 second. So this is what we understand by the classification of the power system stability part. So now let's see the next part. Now let us define the terms one by one in the small signal analysis. So when we consider the small signal analysis, we have to consider a few definitions associated to it. I'll go by one. You all please note it down in your copy so that it will help you to remember the things. And whenever you will require to attempt some of the questions associated to the multiple choice questions in a competitive exam or in any other exams, it will be of help to you. So let us see the first definition. The first definition is the stability limit. So how do we define a stability limit? So stability limit is the maximum power that can be transmitted to the specified location in the power system under specified operating condition without the loss of synchronism or in bracket stability. So like if we say that the power station is situated uh, at a distance of 100 kilometer from the load. So how do we define this stability limit? The stability limit will be defined as the maximum power that can be transmitted to the specified location in the power system under specified operating conditions. Like if you have a 100-kilometer length of the transmission line and there is a specified voltage rating of the transmission line, because we all know that the transmission is done at a level above the 11 kV. So above the 11 kV, let's say 33 kV, 66 kV, 132 kV, and so on. So when we transmit the power from the generation station to the distribution end, naturally we will require a transmission line, and then we will require a step down transformer at the substation level, and then this transformer will step down the voltage from a high voltage to a preferable voltage required at the customer end, and in that way the load will get catered with the generation station. So this is how the system goes. Now when we want to analyze the stability of this transmission line of 100 kilometer, we have to analyze with the help of its maximum power transfer capability. So maximum power transfer capability, we will come to it in after some slides in this lecture. At that time, we will see what is the power transfer capability of a transmission system. So we are talking about the stability limit. So the stability limit is defined as the maximum power that can be transmitted to the specified location. Let's say the 100-kilometer, you have a location A and B. A is the generation station and B is the load end. So from A to B, if you want to transmit the power has a maximum limit. So the maximum power that can be transmitted to the specified location in the power system without the loss of synchronism. That is, the system should be in synchronism. That is, the generation station and the load end both should be in synchronism with each other. This is called as the stability limit. Now, the stability limit is the maximum electrical load of the system under the condition of energy input reaching the threshold value with the system still operating at equilibrium. So, as you all know that whenever there will be changes in the load, like if there is a substation and the capacity of the substation, if I say that the capacity of the substation is 80 megawatt, and the load end of the substation which is running that particular load is say 50 megawatt. So all this 50 megawatt will not be required at a given moment of time, or in other words, this 50 megawatt is the peak power. We are talking about the peak power. So this 50 megawatt will be there at a certain level in a day or night or in the complete 24 hours of the time. But this peak will not be there every time in the day. So whenever this peak will reach at that time, if 50 megawatt is not reaching to that substation, then there will be a loss of synchronism, or the system will not be in a synchronism because the load is 50 megawatt, and if you are getting the input energy as 40 megawatt, then how the system will remain in synchronism? So there will be an unbalance, and this unbalance will create a stability parameter, and this stability parameter is called as the stability limit. So we are talking about the threshold value. So if the substation is designed for 50 megawatt, what is the threshold value of that substation beyond which it cannot cater the stability limit? So this is what we understand by the stability limit is the maximum electrical load of the system under the condition of energy input reaching the threshold value with the system still operating at equilibrium. So, if I say that the transmission line, the capacity of the transmission line is 11 kV, and we are loading the 11 kV line with say 10.99 kV, and if still the system is remaining in synchronism, if the system is still operating at equilibrium condition, that we will call that is the stability limit of that particular transmission line. So this is what we understand by the stability limit. Next, we have a next major definition as the steady state stability. So what do we mean by a steady state stability? So steady state stability is the ability of the power system to maintain synchronism between machines within the system and external tie lines for small and slow normal load fluctuations. So it is the ability of the power system to maintain synchronism between the machine within the system and external tie lines. So just now I have quoted the same example. So if you have a point A and point B, point A is the giving the power and point B is covering the loads. So when the point A is giving the power to the load and B, and if there is if after a small disturbance also it is working in the synchronism, and there is a synchronism between the machines and the external tie lines, then we can say that that type of stability is called as the steady state stability. So the underlining point here in steady state stability is for the small and slow normal load fluctuations. So we can term this steady state stability only and only when the system is undergoing a small and slow normal load fluctuation. So if there is a normal load fluctuation in the consumer end, so at that type of the stability, we will call it as the steady state stability. Next, let us see what are the other set of the definitions. So the next state is steady state stability limit. So what do we mean by a steady state stability limit? So it is the maximum power that can be transmitted to the point under concern without the loss of synchronism, subjected to a slow sustained increase in load. So this is what I have said. If there is an increase in load, like I have said that if there is an increase in load, say for the complete day you are having a load of 40 megawatt, but suddenly if there is a rise in the load to say from 40 to 50, and still if your system is working in synchronism, or still if your system is in the equilibrium condition, then that steady state limit will be called as the steady state stability limit. So I will repeat once again the parameter which we have said just now. Steady state stability limit is the maximum power that can be transmitted to the point under concern without the loss of synchronism subjected to slow, sustained increase in the load. So if there is a slow and sustained increase in the load, and still if the system is in equilibrium, or if the system has not lost its synchronism, then that limit we will call it as the steady state stability limit. All these definitions are very important. These definitions are asked many times in the competitive exams as well as in the other exams. So you all should note all these definitions very seriously, and you all should understand these definitions thoroughly so that it will help you to give any type of examinations related to the multiple choice questions as well as the descriptive type questions. Next definition is the dynamic stability. So talking about the dynamic stability, it is the ability of the power system to remain in synchronism after initial swing until the system has settled down to its new steady state equilibrium. So after initial swing, what do we mean by this is that if there is a sudden rise in the system, or if there is a sudden rise in the voltage level or the current level, and after that sudden rise, there will be a next settling point or next equilibrium point, and to the next equilibrium point, if your system is still remaining in synchronism, if it has not fall out of synchronism, we will see what is the remaining in synchronism and what do we mean by out of fall of the synchronism in a very short while. Uh, so if after the sudden increase or after a initial swing, if the system is taking a new steady state equilibrium, and after that also if the system is remaining in synchronism, that type of stability we will call it as the dynamic stability. And the dynamic stability limit is the stability limit is increased from the use of automatic voltage regulator and speed governors. This limit is called as the dynamic stability limit. So this is what we understand by the dynamic stability limit. Now let us take one example, and with the example you will understand what exactly this stability limits has to do with the system. So many times you might have encountered with a problem at your home that suddenly the voltage becomes very low, and particularly this happens in the summer season, because in the summer season the load requirement is more, because of the heat in the atmosphere, we require the air conditioners, we require the water coolers, and because of this there is a huge increase in the load. Because of this huge increase in the load, what happens is the voltage of the magnitude of the voltage becomes lower, and the voltage regulations become very poor. Because of this reason, what happens, there is a voltage fluctuation at our home. And when these voltage fluctuations are there at our home, generally we connect the delicate or the sensitive, not delicate, the sensitive devices such as the refrigerators, air conditioners. We connect them to the home and we connect all these sensitive devices with the voltage stabilizers, right? So why do we do that? Because we need to protect all these sensitive devices. All this equipment are costly, and all these equipments, if these equipments become damaged, then it will take a lot of rupees to buy again the equipment. So our equipment should not get damaged. So for that reason, what we do, we apply the voltage stabilizers to all those systems in order to protect the voltage drop downs, or if there is a high voltage in the system, then also that stabilizer can balance the thing. For that reason, we apply the voltage stabilizers to our this sensitive equipments or the costly equipments in order to protect them from this type of the initial swings. So what do we call this initial swing? Whenever there will be a very sudden initial swing, and if the system is taking some time to settle down and still the system is working fine or the system is in synchronism, then we call this as the dynamic stability. So you will see that even though there is a very low voltage drop down into the system, still there is no power cut into the system, or there is the still power supply available in the system, which is coming from the feeder, which is there in the substation. So that limit is called as the dynamic stability limit. And this dynamic stability limit, when we use this, there is a automatic voltage regulators and the speed governors which limit the dynamic stability limit. We will see this, what is the speed governor system which is there in the generation part, and also the automatic voltage regulators at the generation end. We will come to it one by one. So this is what we mean by the dynamic stability limit. Now let us see the large signal analysis or the transient stability. This In the previous slide we have completed about the small signal analysis. In the small signal analysis we have the steady state stability and the dynamic stability. And in the large signal analysis we have the transient stability. So now let us see what do we exactly mean by this transient stability. So, whenever the system is tested and analyzed for its stability following a large and sudden disturbance. So, the disturbance which occurred a few days back, we have taken the case study in the class also. The Padge line which fall out of synchronism, and there was a blackout in the Mumbai region. This case study we have already seen. So, that type of stability will be termed as the transient stability. Why? Because there was a large and sudden disturbance into the system. We cannot call such type of stability as steady state or dynamic stability, because this fault which had occurred was not a small fault, or it was not a very a fault which has rectified within a very short span of time, and again the system went into the synchronism step. But that it was a very large disturbance, it was a very sudden disturbance. The line was out of synchronism for several hours. So that's why that type of stability falls under the category of the transient stability. So whenever there are short circuits within a very fraction of second, at that time this transient stability will occur. Clearing of the fault, whenever there is clearing of the fault, at that time also we have to analyze this transient stability. Then when there is a sudden change in load, at that time also we have to analyze this transient stability. And if there is a loss of lines which happened in few days back in the Mumbai link, Padge Mumbai link, we have already analyzed it, there was a loss of lines. So all these things comes under the transient stability category. Okay. Now, let us define then the duration to which we will consider. So, we have already seen in the classification part that the duration will be due to the severity of the disturbance. The analysis is carried for a short duration, which is up to 1 second. Then we define the transient stability. So, this is the definition of the transient stability. Transient stability can be defined as the ability of the system to remain in synchronism during the period following a large and sudden disturbance. Even if there is a large and sudden disturbance, and even if after that also, if the system is remaining in synchronism, that type of stability will be called as transient stability. And the last definition which we need to understand in this portion of the transient stability is the transient stability limit. So the transient stability limit is the maximum power that can be transmitted through the system without the loss of stability under the sudden and large disturbance. Excuse me. So this is what we mean by the transient stability limit. So everyone please note down all these definitions.
So this was all about the transient stability. So far we have covered the two types of stability. One is the small signal analysis, in which we have seen the steady state stability and dynamic stability. And now we are analyzing the large signal analysis. And in the large signal analysis, we are analyzing the transient stability. So that again, we will quickly summarize the definition of the transient stability. So transient stability is the ability of the system to remain in synchronism during the period following a large and sudden disturbance. Transient stability limit, the maximum power which can be transmitted through the system without the loss of stability under the sudden and large disturbance is called as the transient stability limit. So all these definitions are very important. This definition can be asked in any examination. You have to be thorough with all these definitions. So now let's next see the power angle curve and transfer reactance. So for quite a long time, we are repeatedly going through the terms called synchronism, synchronism. So what exactly this synchronism means, and what exactly this it means out of the synchronism. Let's understand that first, and then we will see what is the power angle curve and the transfer reactance. So as you all know that we have the most of the power which is coming to our system is coming through the conventional power system, that is through the thermal power plant, wherein we have a turbine generator set, and this turbine generator set gives us the power. That is the when this turbine will be working in a working condition, it will be coupled to the shaft of the generator, and it will then generate the power. So you all know that generator is a moving device, and generator has stator as well as rotor. So also you in the machines, you all have electrical machines. You all have already gone in detail with the working principle of this generator, wherein you have the stator, rotor, and there are various phenomena which are associated with this, like armature reaction, and this there will be the three phases of this rotating magnetic flux, and because of this three different magnetic rotating flux, you'll have the three phase generation of the power, right? So whenever we will talk about the rotor, this rotor will have a angle which will be associated with the stationary reference axis as well as the rotating reference axis. So whenever there is a disturbance at the load end, because of that disturbance, there is a change in the rotation in the rotor also, and the change in the rotor with the change in the load side, this we will define with the help of the power angle curve. So the power angle curve describes the variation in real power for the variation in load, power, or torque angle. So whenever there is a variation in the load, there will be a variation in the power or the torque angle also, and this variation is described with the help of the power angle curve. Let us see a typical single machine infinite bus system, because as you all know that the power system is a interconnected power system, and this power system is having many generation stations there, and many distribution stations. So we cannot draw those many power stations into on this paper with the help of pen and paper. So we are representing the single machine infinite bus model in this way. So there will be a single machine which will be having an EMF of E. There will be a transmission line, and this will be an infinite bus. So this model we will call as the single machine infinite bus model. Let us see then the power curve of this single machine infinite bus model. So this is how we have the curve of the single machine infinite uh, bus system. So on the x-axis I have taken delta, and on the y-axis I have taken the power. So you can see here I have written here PM and this is PE. So PM is the mechanical power and PE is the electrical power. So these are very important concepts. Please understand all these concepts, then it will be easier for you to understand the stability parameter. So as I have already said that most of the power plants we have, the power comes from the conventional power plant. So when the power comes from the conventional power plant, we have the generation available at the in the power system, and when this generation will be available in the power system, we have a turbine generator set. The turbine is having the mechanical power output, which is being fed to the generator, and this generator is giving us the electrical power output. So this is what we mean by PM and PE. Is it clear, everyone, what is the meaning of PM and what is the meaning of PE? PM is the mechanical power which will be there in the turbine, and PE is the electrical power output which will be coming out from the generator. So if we plot the curve, you can see here I have drawn a curve here. This curve will be called as the power angle curve. So you can see here as the delta goes on increasing, the PM also goes on increasing. So the maximum which is achieved is at delta is equal to 90 degrees. So as we again increase the delta from 91 to 180, the PM falls continuously and it becomes zero at 180 degree. So this is what we understand from the power angle curve. So in the power angle curve, it can be seen that the maximum steady state power PM occurs when delta is equal to 0. The total reactance X, which directly connects the two EMF sources, is known as the transfer reactance. So this is what we define by the transfer reactance. So the total reactance X, which directly connects the two EMF sources, is known as the transfer reactance. Now, when we call the equation for the steady state power limit, this is what is the equation available with us. That is, Pm is equal to mod of E multiplied by mod of V upon X. So this is the equation for the power transfer capability equation, which we have stated just now. Before a few slides, we have talked about the power transfer capability. So this is what we mean by the power transfer capability, mod of E mod of V upon X, where this mod of E or the magnitude of E is nothing but the EMF of the generator or the generated voltage, or in other words, we can call it as sending end voltage. So we can also denote this by ES or VS because this will be the sending end voltage. Let us go back to the previous slide and let us see what exactly this will mean. So you can see here we have drawn here a model of the single machine infinite bus. So if we want to feed the supply to this bus, naturally we will require the power. Without the generation EMF, there will be no supply which will come to this bus. So that's why sending end EMF or sending end voltage is very, very important. Without the sending end voltage, we cannot get the receiving end voltage. So this is what we understand here with this equation, mod of E mod of V upon X. Mod of E is the sending end EMF or sending end voltage. Mod of V is the receiving end voltage or the receiving end magnitude, and X is the transfer reactance or the total reactance, which is also known as the transfer reactance, which will be associated with the transmission line. So is it clear, everyone, with this slide? This is very important. Everyone, please note it down. This is a very important slide. Many things are given in here related to the power angle curve of a synchronous generator. So is it clear, everyone? Please reply on the chat box. What do we mean by this complete scenario? Has everyone got the point? Just now, what we have understood from the single machine infinite bus system, that is, there is a generator and there is a bus. This generator is giving the sending end voltage to the infinite bus, which is getting the receiving end voltage. If we want to consider the transfer, power transfer, what amount of power will be transferred from one end to the other end, this is what is the equation available with us, that is EV by X, that is sending end voltage multiplied by receiving end voltage divided by X, that is the transfer reactance. So is it clear to everyone? Please reply on the chat box. Okay, very good. So this is what we mean by the power angle curve, and this power angle curve is used to define the stability limit, or the to do the stability analysis with the help of the delta angle. So the angle which we have written here, this is the um, load angle or torque angle. With the help of this angle, we will be able to analyze the things. So now let us see what are the characteristics of the power angle curve. So one by one, we will see the characteristics of the power angle curve. The first characteristic that we are seeing here is the steady state power limit or maximum power limit is inversely proportional to the transfer reactance. So if you will go back to the previous slide, you have here EV by X. So you can very well see that the power is inversely proportional to this transfer reactance. So that is what we have written here about the first point, that is the steady state power limit or maximum power limit is inversely proportional to the transfer reactance. Then second point is series capacitors can reduce the transfer reactance and hence can improve the steady state power limit. So you all know that in the transmission system at various places capacitors are installed. So capacitors are installed with the intention of two purposes. The first purpose is to increase the power transfer capability of the transmission line, and the second one is to have a proper power factor associated with the system. So for these two reasons we install the capacitors. So series capacitors can reduce transfer reactance and can improve the steady state power limit. Next point is for transfer of electrical power, reactance is compulsory. It should not become zero. Alright, so is it clear? So reactance should not become zero if we want to transfer the power from one end to the another end. Now you all know that in a transmission line, in the power system one, you might have learned about the various parameters of a transmission line, that is resistance, inductance as well as capacitance. So the transmission line will have all these three, but when we talk about the reactance, there should be reactance available to the transmission line. Without the reactance, there will be no power flow from one end to the other end, because you can see here we have the equation available with us, that is EV by X. So just you can imagine, if this X becomes zero, what will happen? So can anyone reply what will happen if this X becomes zero? What will be the resultant to this power equation? So if we replace this X with zero, what is going to happen? Anyone can reply? Okay, infinity. So it's a condition wherein there will be no power flow from one end to the other end. So that's why what we can say that the for the transfer of electrical power, the reactance is compulsory. It should not become zero. Now the next point is very important. This may be asked in many question papers related to the competitive exams or other such things. So you have to remember this. So for transfer of electrical power, resistance is not necessary. However, the condition for PE to become maximum occurs when x is equal to root 3r. So if x is equal to root 3 times of the resistance of the transmission line, in that position we can say that there will be a maximum transfer of the electrical power from one end to the other end. So is that clear to everyone? Please note all these points. Then we will see one more point associated with it, and then we will see a question related to the gate examination, a theoretical question which was asked many times um, in many of the examinations. So is it clear, everyone? Has everyone noted down all these points? Shall we move to the next slide? Okay. So here we are going to see one more power curve. So you can see here I have given here two different power curves of two different generators. So at a particular power angle delta, if transfer reactance is reduced, the power transferred in the system also increases. So you can see here I have given here two different curves. So the curve first one and the curve second one. So you can see here when we have reduced the transfer reactance, so if the power transfer reactance is reduced, the power transferred in the system increases. So if we reduce this x2, that is x2 is less than x1, then PE2 is greater than PE1. From this chart you can see here, this is PE1 and this is PE2. So this is the PE part. So the PE part increases with the reduction in the transfer reactance. So this graph is showing the increase in power transfer capability, or the increase in the power transfer when the transfer reactance value is reduced. So please draw this diagram, and once completed reply on the chat box. We will go to the next slide and we will see a question related to the gate examination. So is it done? Has everyone drawn the diagram? What this diagram is indicating, that if we reduce the x, then the power transfer capability increases for the particular system. So that's why the transfer reactance has to be reduced to its minimum level, so that the power transfer capability can be increased. So is it done? Shall we go to the next slide? Okay. So next portion is swing equation. We will see it at other time. Next we will take a gate question which is asked in the gate examination related to this topic which we have just now learned. After that we will on the next lecture we will see the swing equation and the questions associated to it. So the question is in this way. So please note down the question. Steady state stability of a power system is the ability of the power system to. So the options are available with you. So I expect a quick answer from all of you. So everybody should be able to reply to this question. Please reply to this question fast. Uh, just now we have learnt about the steady state stability, right? So we have just now learnt about the steady state stability. So what will be the correct answer for this particular question? So what will be the correct answer to this question? Is the question clear to everyone? Steady state stability of a power system is the ability of the power system to A. Maintain voltage at the rated voltage level. B. Maintain a frequency exactly at 50 Hz. C. Maintain a spinning reserve margin at all times. And D. Maintain a synchronism between machines and on external tie lines. So, okay, few of you have replied. So I expect a reply from everyone. So see, everyone is able to reply correctly. Yes, D is the correct answer. D is to maintain a synchronism between machines and on external tie lines. So see, you all have answered a gate question. So this question was asked in the gate question paper in summer 2000. Sorry, not summer. In the gate question paper of 1999, as well as after that also it is asked many times. So see, you all are able to reply a question which is asked in the gate exam. So this is what we require. This is what is required at everyone's level, that you all should be able to know what is there in the basics, what the basic definition says about the stability part. So you will be able to attempt the questions which are asked in the any competitive exam related to the electrical engineering stream. So tomorrow we are going to see the swing equation and few questions associated with the swing equation. This we are going to see tomorrow. So now we open the forum for discussion. So if there is any questions related to any part, so I expect everyone to have the question.